Okay, so we started off with electrostatics. So this term, we're going to begin with magnetostatics. And then once we studied electrostatics, we talked about chapter 4 in particular was dielectric materials. So after magnetostatics, we're going to study magnetic materials, and then we're going to do electrodynamics. We're going to study how the electric field can create a magnetic field and vice versa, and electricity and magnetism will be combined. And we'll have electromagnetic waves, simple things that we know from high school will be derived after a lot of effort, like law of reflection and refraction. Reflection, the angle of incidence and the angle of reflection is the same, but now it's derived. We don't, because we know how electromagnetic waves behave.
For the magnetic materials portion, I know that a lot of magnetism at like the material level goes into quantum explanations and things like that.
Yeah.
How will we?
Right. So that's a good question, and you must have read ahead to know the issue. But because it is true that a magnet, for example, a ferromagnet, a permanent magnet, that's a quantum mechanical effect. There are two ways to discuss it. One is to describe the general property of how things become magnetized. The other one is there is an effective set of field equations for magnetic materials. Well, not magnetic, I'm thinking of superconductivity. But so we won't get into either quantum mechanical or superconductivity, but to some extent, those are probably a detail that is not important at this point. We'll still know how the stories put together, but to understand the effects more carefully, you have to know quantum mechanics. And I'm assuming both of you are taking quantum mechanics next year?
Fall. Yeah.
Fall, yeah. Okay, so let me start off with a quick recall. If you have a charged particle in an electric field, what is the electric force, the electrostatic force on the charge? Q times E, right? But you can imagine, we're familiar with magnetism, you've taken physics too, so we don't have to talk about magnetism being a mysterious quantity. And you may even recall the formula. But one of the most important features of a magnetic field is, suppose you have a magnetic field and you have a charge that is not moving. It does in a certain frame. In that frame, certain inertial frame. In that inertial frame, there is no force on the charge. If it is moving, there is a force on the charge, and it depends on the magnetic field. The direction of the force is perpendicular to the magnetic field and perpendicular to the direction of motion. When you have a third vector that is perpendicular to two other vectors, you know it's the cross product. So, in some sense, and I suppose this could be combined. This is called the Lorentz force. On a charge. So you have to do your V cross B very carefully. So let's do a simple V cross B problem that you have seen before. Suppose you have, this is the cyclotron, right? So suppose you have magnetic field into the board. And you have a charge over here moving. And the magnetic field is everywhere, so let me move this from its location. You have a charge here moving with speed or velocity v as shown. which way is the magnetic force on this charge?
Is X in or out?
Right.
X is in.
I know what you mean.
V.
Yeah. Correct? V cross B. Yeah, I don't know if you got the direction right. It could be X, positive X, negative X, so to speak, but you have to do V cross B. Use your right hand. Yeah? And I'm ignoring the electric field because there's no electric field here. And in this chapter, that's not the purpose. We won't consider electric field. I just mentioned it just as we got started. So this charged particle feels a force in this direction and turns around. Let's say the charged particle is somewhere here. And I am almost influencing your mind because I know the answer and you've seen the answer before. Which way is the force now? Say right, left, up, down. Down. So you know this is sort of a centripetal force. And this charge is going to move around in a circle. And centripetal force, mv squared over, let me call this r, whatever this radius is. That's the centripetal force, and that's equal to qb. That's the balance. So I can then write this as V over R equals QB over M. If things are moving in a circular path, there's a relationship between velocity and angular velocity, omega. Do you recall what that is?
R cross omega is V.
V in magnitude, V is nothing but R omega. And here indeed, you get omega equals QB over M. This is called a cyclotron frequency. CY. Omega is nothing but d theta over dt, rate of change of angle. It's the angular velocity. You know, as the charged particle moves in a straight, along the circle, it sweeps an angle, the rate of change of the angle. So here I'm, of course, using V equals R omega. So typically in particle accelerators, a simple magnetic field will allow charged particles to move in a circular path, and hence you have these circular particle accelerators. I haven't told you the whole story. You will see, if we make it that far, I think it's chapter 11, that when charged particles accelerate, and you know it's accelerating because it's changing direction. When charged particles accelerate, they also radiate electromagnetic radiation. Therefore, as this is moving around, it loses energy. So you have to kick it back up for it to go into a circular path. Otherwise, you will find that the path looks more like this. So in particle physics, very often you'll see there's a bubble chamber where it records the tracks of particles, literally just physically making the track, and you'll see diagrams very often like this. this is a telltale sign of a particle-antiparticle pair. One is positively charged, feels the force one way. The other one is negatively charged, feels the force the other way, and it spirals as it loses energy. Okay? But at this point, from what we have learned, we have no way to include those effects. So we're considering it that it's just moving this way. You have seen this in your modern physics lab. You have seen the E over M experiment where there's an arc. Yeah? You turn on the magnetic field and the radius of the arc changes. And in that case, in that lab, the arc pretty much did look like this. It was not enough time to lose sufficient energy to where you can just visually see that it has actually deviated from its circular path. So it did look, and they kind of both look like circles of different radius. So when you looked at it, well, you did see a circular path. But remember, if you sustain it for a while, they actually lose energy, and you have to accommodate that. And that's not an easy problem to solve, although easy enough to write down, perhaps. Okay, so I want to do this also vectorially. Let me make sure that when I place the camera, I could see all the way to the, yeah, perfect. So I want to do this vectorially, all because we didn't use any calculus here, and this is, of course, Griffiths. So and I'll tell you why. I'm going to pick my magnetic field to be so this is X, this is Y, this is Z. If you want it to be a positive charge, let's say the charge Q starts over here, and we know it moves in a circular path. We know it's going to move in a circular path. You'll find that if it's a positive charge, it moves in this direction, as I've shown, only if the magnetic field is pointing downward. We'll see, otherwise we'll have to write it the other way around. So I'm going to write this as B. There's a uniform magnetic field pointing downward. So let's write the force. It's Q times V cross B. Well, so it's determinant, sorry. X hat, Y hat, Z hat. And V, it's nothing but X dot, Y dot, Z dot. And magnetic field 0, 0, minus B. So let's see, first of all, if our diagram is correct. Let me look at the XY plane. This is the XY plane. There's a charge here, and the positive charge is moving this way. If the magnetic field is pointing downward, which is the direction, yeah, so that is this way. And so it'll move. Otherwise, it's no big deal. It's just going to go that way. I just placed my origin on this side. That's why I picked B to be negative. Okay, so let's do this. It's going to be Q times X hat, Y dot times minus B. So Y dot times minus B. Then this is the next guy, so I put Y hat minus Y hat. Then I again have X dot times minus B. Z hat is going to be 0. Too many parentheses. So MA, which is the force, is going to be what? Let's look at the components. Minus QB. What do we have? Y dot X hat. Minus minus is plus, but I have one minus outside. And X dot Is that correct?
Where did our dot notation come from?
Oh, I'm sorry. So-
Got it.
Yeah,
Got it.
so this is V cross B, right?
Mhm.
So,
Representing-
yeah, so
Yeah.
velocity is dr dt. So position is given by x, x hat, y, y hat, z, z hat. So velocity becomes x dot, y dot. Okay, so that means, first of all, look, I'm not going to write it as a second equation. I can put this as q b over m. Once again, I'm just going to save on writing. Make it omega there. A nice feature that you can pull out. And then I have acceleration in the x direction. Let's look at that. So I'm going to write this equation, x double dot. If velocity is x dot, the x component is going to be minus w y dot, minus w y dot. And y double dot is going to be, not w, omega, what did I just say? X dot. And of course, z double dot is 0. Now, you can find a general solution for this. It can be written in terms of sine and cosine, but I'm going to intuitively impose my initial condition. I'm going to go a distance r away along the x-axis. That's where it's going to start. So, I know the answer, you see, and that makes it worse. And this is my axis. This is distance r. So this is x. So I know what I want to do is cosine theta, but theta is omega t. Of course then, y is r sine omega t. Does this even make sense? Because this is the equation of motion of a particle going around in a circular path with what? Constant speed. If omega is a constant, b is r omega, so speed is a constant. That's why I'm cheating. Yeah? So to verify this set of equations, I don't have to worry about z double dot, but verify these two, I have to take two derivatives. So let's do all of that. X dot is going to be minus r omega. Please let me know if I'm doing this correctly. Cosine, when you take the derivative, there's a negative sign. Y dot is r omega cosine omega t, and then x double dot, I get minus r omega squared cosine omega t. Y double dot is also minus r omega squared sine omega t. Let's actually try to see if this is true. We have x double dot. We want it to be equal to, and I'm just going to leave a little space, y dot. Well, let's see if that's true. I have minus r omega squared cosine omega t equals minus omega y dot. And all of a sudden, no, correct. R omega cosine omega t. See, minus omega, y dot. And y dot I just copy. So, yeah, it does work. Let's try the other one. Y dot is equal to, again, let me leave a little space, omega x dot. Y double dot is minus r, omega squared, sine omega t equals omega x dot. It better have a negative sign, and it does, minus r omega sine omega t. That too works. Okay? So what happens is, if you have a magnetic field pointing downward, this charge is going to go in a circular path. Now, what happens, we can easily expand on this guy. These are called coupled equations, right? What happens in x depends on y. What happens in y depends on x. But look at z. So instead of pushing it in the xy plane, what if I gave it a little push that way? The z velocity is not going to change because z acceleration is 0. So instead of a circle, I get a nice helix. Yeah? That's what happens. Oh, I should. Your book has, the book doesn't do this with differential equations. It does it just by mv squared over r equals the force. I did it with differential equations, but the next one is a magnetic field and an electric field. There's a worked out example, so I didn't want to work that. But this prepares you for that one. I would like for you to go through example 5, I'm guessing 5.1. That is worked out carefully. In doing so, let me see. Oh, sorry, example 5.2. Carefully. In doing so, I would like for you to make sure you can derive equation 5.6 from 5.5. If you have questions, you should come and talk to me. He has provided a hint, and when you look at the hint and stare at it for a while, it'll work easily. You have to make a couple of substitutions of variables. That's the tricky part. But I would like for you to endure the calculation and go all the way and read the example. Magnetic fields are like students.
Where does this one go?
They do no work. Present company excluded, of course. So let's do this. Bye. Well, it is F dot dr. Yeah? So let's look at this. It is Q V cross B. Oh no, Q is not a vector. Dot dr. let me do a little calculus change of variable. I can do it as dr dt. I can put the q outside. V cross B dot V dt. What do you notice? What kills this? The answer, I told you the answer. Magnetic fields do not do any work, so the answer is 0. Something is happening. Why is this 0?
The outcome to the cross product will be perpendicular.
That's exactly right. This is both perpendicular to V and B, but what's interesting to us is it's perpendicular to B. So when you do this dot product, you would get 0. So magnetic fields do not do any work. That's odd. I've played with magnets before. Okay, although you're familiar with this, I would like to talk about electric current. So let's think in terms of simple terms. Suppose you have a conducting wire and you just place a mark. And you see how many charges are flowing across. Remember, this chapter is magnetostatics, which means it's not quite electrostatics, so charges are free to move. And when charges move, you'll get an electric current. You're familiar with this from physics 2. So current is defined to be the rate of flow of charge. So it's measured as 1 coulomb, the metric unit, per second, which we write as 1 ampere. Okay, so let's try to physically understand the expression for current. Let's say charges move with some speed v. So charges move with some speed v. It's the magnitude. We know it moves along a conducting wire. And then you wait for delta t seconds. So in delta t seconds, let this be the distance dl, small differential length. It's nothing more than v times dt. Every bit of charge contained in this much portion of the wire, every bit of free charge that is flowing contained in this portion of the wire will cross our mark in delta t seconds. Well, how much charge is contained in this much wire? Well, that's easy. dq is nothing more than lambda, which is linear charge density. Linear charge density of flowing charges, not times dl. Or this can be written as lambda times the velocity times dt. That's dq. Well, current is dq over dt, or lambda v. So let me write that. It's a simple equation. The current flowing in a conducting wire is lambda, which is the linear charge density of the charges that are free to flow. Now, why are charges moving along a conducting wire? Well, maybe there's a battery. It's connected to a battery. It just pushes a current. Okay, and this is the expression for current. Using this, I would like to calculate, suppose you have a current carrying wire in a magnetic field. You would like to know what's the magnetic force on the wire. So, magnetic force on a current carrying conductor. So recall for a single charge, I'm just looking at magnetic force, it is V cross B. So when you talk about a long wire, obviously we're going to compute the force along some small portion dl, and I can even make this a vector, and then add it up. So this is going to translate to an integral. Well, F is equal to, well, for the small portion, how much charge is contained in that portion? Well, we just talked about it. It's lambda times dl, and then V cross B. What we will do is a little bit of symbolic rearrangement to get the expression in useful and meaningful way. So I can write this force as lambda dl V cross B. Now I'm going to do a little shuffle. That's an interesting trick. Look, this is the vector dl. But that is also at least the direction of V. Because after all, the charges are flowing along the conducting wire. So it looks silly, but this is what I'm going to do. I'm going to bring this V over here and put this vector on dl. We just talked about this. This is the current. So traditionally, force on a current carrying wire is, remember, the expression as IDL cross B. And this is the expression that we seek. Okay.